Hi everyone, I'm Felix. I work on mainly Deck.gl and also WebGL. I work also for Carto. I have the privilege of having the third talk in a row talking about our transition from WebGL to WebGPU. So I hope I still have some content left that is going to be. If there's some stuff which is similar, I'm going to just skim over it. But just like with its talk, if you feel like asking any questions, then please stop me. The first thing I have in terms of transition is like an illustration by an architecture in London, showing that one, we have sun in London sometimes. So here we
AI?
AI Photoshop. Yeah, I was born in the last century. So, in the forefront, we have more kind of WebGL style buildings, kind of like solid foundations, changing over the years, building up ideas, and then lurking behind them, we have WebGPU, very kind of like rendered in nice even blocks and reaching even higher than before. Okay, so this talk is going to be about some of the differences between two APIs, current status, and then I'm going to dive more into the changes that have been made from sort of my point of view on the Deck.gl side. So what did I have to change in Deck.gl to kind of make this work, whereas it was more talking from the Luma side, what was needed to be built as a foundation to move forward. First off, as it went through, Luma 9.0 is a huge rewrite. We've adopted a much more WebGL-inspired API, but the idea is we still want to support WebGL too. So we want to be sort of thinking in a WebGPU fashion, but still supporting WebGL too. Biggest differences are that obviously the API has just got like different ways of writing things. In WebGPU, we're often strings, whereas in WebGL2, we're using a constants. In terms of like the entire programming model, then this idea of global state has been replaced by pipelines and buffers. And of course, the shade language is different. So first off, the comparison between it looks like writing like GL is we're often just writing to this like global state. I want to bind a texture. Okay, I bound the texture. I want to set this filter on it. I want to bind a buffer. I want to enable it. It's all just kind of writing to some kind of global object. Whereas in WebGPU, it's much more sort of closer to a modern programming model. So we're creating a sampler and we're giving that some properties, and then we can work with this as an object. So one analogy that we can make here is with JavaScript back in 1999. This is a little bit overkill. In fact, there probably wasn't even a map function back in 1999. Now I realize. My code is too good.
It wasn't.
It wasn't, yeah. You just noticed that. Anyway, yeah, this is how you write code back then. You know, you don't need to output sort of anything from a function. You just update the global state. This will work just fine. And for like a small toy application, this can work fine. But today, we more want to look at things in terms of types. We want to kind of build like reusable building blocks and kind of understand what we're putting into a function and what we're getting out. So to make an analogy, which I'm wondering if the joke is going to work here, if you didn't grow up in Britain in the 90s, probably not, but I think at least Chris is going to get this. So in 1999, we had kind of global state everywhere, side effects are fun, and we have no types. And now we're moving forward, and global state is bad, we have types, and we're trying to avoid side effects. Ask me if you don't know who these two people are afterwards. Who knows who those two people are here in this room? That's like 30%. It's Oasis, the greatest band ever that have reformed just recently. So, okay, GLSL. So now just a quick comparison between the two shader languages. Actually, yes, the language has completely changed, but it's not that big a shift. A lot of the things, if you're just looking at the shaders, do appear to be kind of cosmetic. We define uniforms, which are the kind of global kind of parameters that are set across the whole program. Attributes, which are kind of like our row-based data that's being passed in, and bearings, which are outputs that are being passed between the different stages of the graphics card. So from the model stage to the shading stage. And then we finally have the actual program itself. So here I'm just setting the position of the vertex by multiplying some kind of matrix, which is specifying like how the camera is looking, and setting some kind of color to an attribute that's coming in. If we look at this in WebGPU, broadly speaking, apart from lots of extra fluff around it, it's the same kind of idea. We're still passing in uniforms, we still have an input and output, everything is renamed, but if you kind of squint, it more or less looks the same. So yeah, the syntax changed. The passing between vertex and fragment stages is basically unchanged. Here I'm talking about like larger architectural levels, not the actual syntax. The attributes, they're still basically similar. What is different is that the uniforms, and Ib mentioned this before, and I'm going to focus on this, they can no longer be global. So in GLSL, we write out each uniform separately and set it separately, but here we're passing in an actual type struct, camera uniforms. We're passing in some kind of a block of memory written to, and then we've bound on to we've sent to the GPU. So here we have a problem between the two APIs, and we had to find a way to sort of bridge this difference. Luckily, in WebGL 2, we have something called uniform buffer objects, which look very, very similar to what we have in WebGPU. So these allow us to set a bunch of uniforms in one block, and thus also avoid having to call the set uniforms function again and again and again. But the big difference is that it allows us to structure our applications in the same way, irrespective of if we're targeting WebGL or WebGPU. So this lets us have a WebGPU like API in WebGL, which is great. Downside is we have to port all the layers. We need to drop WebGL 1, but we get a performance benefit, and this previous talk. So the question is, how do we actually do this in a way that it's kind of nice for the application developers? So what we have for this is this concept of a shader module. And this is actually nothing new. We've had this in Deck.gl and LumaGL for a long, long time, but it's been often quite hidden below the surface, partly because it's been used for not as many things. It's been used for, say, like the projection or something. But if you're writing a custom layer, you wouldn't often need to use the shader module. But this is changing with this new version. So I thought it'd be useful to go over how this works and how we can use it in new layers. So at a high level, shader module is some kind of encapsulation of functionality that's going to let us inject some shader code into a large program, and also set like parameters or props in this case from the JavaScript world onto the GPU. And because it's all typed, it also makes it prevents us from making a lot of very, very hard to debug mistakes. As you can imagine, if you just write into some memory that you're then going to bind onto the GPU, and you don't get it quite right, you don't align the memory right quite in the right way, you're not going to get like a nice error. You're just going to get a black screen, or you're going to get some weird artifacts. So here it really helps to have some kind of type safety to get us through. So the way we use a shader module is at some point we define it. This is a very abridged version of the API. The main thing here is that we've defined some custom props which are going to specify our interface into the module. Then when it comes to a Deck.gl layer, then every layer has a function called getShaders, where we actually retrieve the vertex shader, the fragment shader for this layer. But we can also inject shader modules. So here we can inject any kind of custom shader module, and it's going to add the code of this module for us. And then when it comes to drawing the layer, then instead of setting uniforms like we did before, we're going to set props on the model that is using this module, and we're going to specify that we're updating this specific custom module. I think I basically went over a bunch of these. Yes, the important one is this uniform types field. which is specifying the layout of our uniform buffer object. So that's here, and I didn't actually, I'll come to the later slide. There's more advanced ways that we can use this shader module. There's a getUniforms function, which can be used for more complex transformations. I'll get onto that later. But the nice thing that we have here is that this module is going to automatically split uniforms, which are things like numbers, arrays, just like more sort of simple objects, for bindings, which are textures, when it passes it into our shader code. Okay, so to give this a little bit more shape and clarity, I'm going to go through porting a layer that I worked on in Deck.gl to UBOs. So we actually have a concrete example rather than looking at just an abstract definitions. So again, I would reiterate what Ib was saying before, like with debugging this kind of programming, sort of like shader programming, graphics programming, it can be very easy to kind of end up with like a black screen or something going wrong. So as a first step, it's always good to just open whatever layer we're working on and have some kind of reproducible kind of playground where we can just mess around with it. So this is actually, for those who don't know, there's a sort of sample app in Deck.gl called the Layer Browser, which lets you go through all the different layers, set different parameters on it, and play around with it. And it's actually very useful when developing and testing out new code, because you can just quickly check, is my layer doing what I expect it to do, without having to build your own sample app. Okay, so the process of porting, first of all, we need to identify what uniforms our layer is using and which we need to port. So in the case of the PointCloudLayer, we have the opacity, radius, and size units. And in general, we also want to look at the fragment shader and also check if we have any textures that are being used. But in this one, it's a simple layer. For an example, we're not using them. The first one, opacity, is actually very easy because this is being handled on the layer level. We've already kind of ported this, and every layer, all it has to do is rather than using opacity in its shader code, it can just now use layer.opacity and it's going to work. So we can just skip that one. That's what I'm doing here. Somewhere in the shader code in PointCloudLayer, we have a line of code where we're using opacity, where we're setting the color. So instead of using opacity that we're passing in on a global level, we delete that and just use layer opacity. We go back to our layer browser and we check it works, and it does work. So it's good. We can keep going. This may seem obvious, but the number of times I went back to this and it didn't work, it was very high. So I developed this thing of doing it again and again and again through all of the layers that I went through porting in a Deck.gl, and it pays off to do it this kind of sort of idiot-proof way. Okay, so the next step, and this is the more interesting part, is defining a shader module to inject these uniforms. So all we need to do here is define like this uniform buffer object. So that's these 4 lines of GLSL that we have here, which are not syntax highlighted, I'm sorry. And we're just writing in a slightly different format. We're telling the shader that we want to have two uniforms being passed in this UBO, the radius pixels and the size units. And then in the shader module below, we have to specify the types of these uniforms. And this here is like very important. Like if you don't get these types right, it is just completely not going to work. It's like writing a flow into binary memory and getting out an integer. And that was one of the times I wasted 4 hours of my life. There's just nothing there. I change an I to an F and it works. And I slam my computer down and I go out and have a beer because it's tedious. Then we add types. And this is kind of from this frustration came this next part. Is that we have a system now built in which does a type cross-check between the types that you're passing in from JavaScript world and these uniform types that you're setting within this shader module. We don't have a cross-check between the actual shader code and the uniform types because it's just a string, but at least here, if you set your uniforms types in the correct way, then we're going to cross-check between what you're passing in from the outside to what this code is expecting. Just to give an example here, then if I go on radius pixels and misspell it, then it's going to instantly complain, well, that's not right, because in my props that I want that to be spelled correctly. If I go and delete this, it's going to complain, well, you forgot to add a size units prop. If I, on the other hand, give that prop back and add, I think, just some random prop to this, it's again going to say, look, you forgot to add this prop. And it's even smart enough to understand if I'm going to pass, rather than just a 1D number, I'm going to pass in a 2D array. It's now going to complain, okay, but this unit now doesn't match. You can't do that. You have to specify some kind of vec2 type. So if I go down here, and I think if I change it, it's going to show that by auto completion, I can only use one of these three vec2 types. So this is now actually very nice, because if you're going to go into the code base and you want to change a shader module, then the type's going to propagate all the way from the shader module into the layer that you're using up the stack to the publicly typed interface of this layer.
Beautiful TypeScript.
Yeah. It was Xiaoji's idea, and then I had some playing around with it. But yeah, I like it. It is good, and it has saved me some times. I'm not sure how much of the code base I ported before I had the helper. Yeah. Not always do you get to do things in the correct order.
Is there a way to kind of generate the types from the shaders code?
We did consider, so you're saying, is there a way that I could get this uniform block automatically?
Or the other way around, get the type from the uniform?
We did think about it. We decided not to do it because it was a bit too much magic at this stage, and we'd rather port the code and understand what was going on and then add the magic maybe later. But at the moment, no. That's the one kind of sort of missing part that you have to be careful. And also the order is important. If the order is wrong, it's not going to work. So that JavaScript object has to have it as the same order up there. If you swap it around, it's going to get swapped around in memory, and it's going to be a bad day. So yes, there's definitely scope. I would more go down the way of the forms from that uniforms type object. It looks like it should be doable, right? It looks pretty similar. But at least this way, it's kind of explicit. And these files end up being generally quite simple. Like there are a few lines of code. And
another option is we do pass the it on WGSL. We do have a parser that passes the WGSL code and gives us information about the structure declarations and so on. So we could validate those path declarations against the shader module.
Yeah.
We could issue a runtime error.
That would be runtime, yeah. Yeah, that's true. There are definitely things that we could do, but at least this way is simple and gets us where we need to be.
Would it help with differentiating between floats and numbers if they were float array and integer array, like even for single values?
Potentially, that is true. Like the one part of this type cross-checking is if you're passing in an integer or a float, then JavaScript doesn't know. And actually, if you're passing in a Boolean, then you actually have to have an F32, which is a bit confusing. So I think yes, that could help. But at least for the kind of dimension, then this is going to help you out. Yeah. The trouble is that there are just a lot of props in Deck.gl, and if you decide to say, oh, we're going to be passing ints rather than just numbers, then you have to go and change the entire code base. So it's trying to make the code base more type safe while not exploding the problem, and also not making it not making it visible on the public API. Like we're trying to make it easier for people to use and say everyone now you have to actually say it has to be an integer.
If there is a number and I pass a float inside, but it's declared as an integer, does it decrease the precision and it works, or?
I think it's just going to be cast on the JavaScript side before it gets sent there. Okay. JavaScript's not really differentiating between floats and integers. Only once you put it in this array, yeah.
If you've got like a buffer which is a typed array, a sort of uint32 array or whatever, there the type, that's sort of a separate question in the type system.
I think
like a deck of you know, F32 or whatever, it could check whether it really is a float 32 array.
Yeah, I mean, from the outside, is it really helpful to the user if you force them, when they want to specify, you know, just numbers 0 and 1 to wrap it in a, like,
Problem with typed arrays is that they have no static length information. We can validate number by using these arrays.
yeah, that's true as well. Yeah. Yeah, a big part of this is it's counting how many elements you have in the array, and then it knows if it's going to be, because that's the most common mistake you're going to make. You're going to write vec2 instead of vec3, and then it's all going to go wrong. It's very, very easy to miss. Okay, and then to integrate it, then we just need to modify this getShaders function and add the module, and this is going to inject the code for us. And when it comes to actually drawing a layer, then this is the old style way where we're just setting the uniforms, and these are being set on the global state. Instead of that, we're going to construct these props. For good measure, we're going to sort of set the type here so we can make sure that what's getting passed in is correct, and then just set this on the shader. And then again, check it works. And of course it works because we haven't updated our shader yet. It's still actually using the old code. But this is actually the good way of doing it, to make sure that everything has been placed in the right place and there's no sort of crashes or something weird going wrong. And then all we have to do is just rename the variables and it should work. So at this stage, all that's required is that we delete the old uniforms and rename these new uniforms with this sort of point cloud prefix space. And then again, we can check it works, and it should. Just a quick note on textures. Those are not going to be put in these uniform types. They get specified in the point cloud props in exactly the same way. And then they get declared as separate bindings in the shader. And the shader module knows how to split these props from the other kind of uniforms and isn't going to sort of complain that you haven't included it in the uniform types. Yeah, so this cross-checking, I found it to be very useful. The general case is that we have just a direct mapping of the names that we're passing into the names in the uniform buffer object, but we can support a much more kind of flexible API via this getUniforms function, which essentially takes the props and maps it to the uniforms and the bindings that the module expects. So here I have an example of a height map module where you only pass in a texture, and then this module is going to be responsible for figuring out the size and width of it, and then passing that into the shader. And to do this in a type correct way, then here you notice at the bottom that I declare my shader module, and rather than just passing in the props, I also pass in the uniforms and the bindings. And what TypeScript is doing in the case where I don't have this, it's inferring the uniforms and the bindings by splitting the height maps props type, and so splitting out the bindings and the uniforms, and then passing that to the uniforms types to do the type cross-check. So some examples of more complex shader modules that we have within the ecosystem of the project, shader module in Deck.gl, and the lighting in LumaGL. And I wanted to just go a little bit into these to show how you can pull these into custom layers, because I think there's some quite cool examples of things that you can do. I haven't seen that one. So I'm going to focus on the lighting module, which is used in a handful of layers. This is just an example from the Deck.gl website, where you can just play around with some sliders to have some nice lighting. This module is automatically in my Deck.gl. But to actually get some lighting effects, we need to include material. So here I'm going to be using the Fong material, which is a pretty simple lighting model, but works well for Deck.gl style layers. And just as a comparison, then the simple mesh layer is already using this. So as you see, as I rotate this, then the colors like on the shoulders are being like shaded. It gives the model kind of some kind of 3D space. Whereas text layer is just purely one color. It doesn't matter how you rotate the camera, it's always gonna look like this, and it's just as sort of visually interesting, doesn't have the same sense of depth. So let's try and integrate this lighting module into the text layer. So to do this, we need to basically get the Phong material and include it in this layer. So I'm going to go through the same process again. First of all, we need to integrate it into the shader. So if I look at a layer that already is using the lighting module, you can see what it looks like. It's actually quite simple. We need to pass in a camera position and the position in common space of this model, and this is something which you just are already being passed into most shaders. And when the layer is finished with its calculations, we just need to call this extra function that's been injected by this module called lighting get light color, and pass these parameters, and it's going to do its magic, and it's going to give us a lit model. And then, much in the same way that we're injecting the module for the UBOs, and the simple mesh layer is including this Phong material here in its modules when it's calling get shaders. So we're going to use the same thing in a text layer. I think I'm running out of time, so I'm going to go quite fast, but these slides are going to be available later. So this is a bunch of details of how to actually upgrade the text layer, because you need to mess around a bit with the layer hierarchy. I'll skip over that and get to the injections. So when we're constructing a layer, we can actually inject data code at certain points with an injection objects we can inject into the shader code at different kind of positions. Rather than adding to the bottom, we can say in our main function, I want at the end for you to add the specific thing, and in the top of the layer, on top of the shader, I want you to add these kind of declarations. So by doing this, we can modify the text layer to first get the camera position and position common space being passed to the fragment stage, and then also set them at the end of the main function. And then this is the modification of the fragment layer, which is going to allow us to reuse this camera position for every fragment. And at the end of the main function, we're just going to modify the lighting color by passing through with the variables that it expects, and hard coding a normal, because we don't actually know what the normal is. We're just going to say the normal is pointing up. This is a flat shape. So if we do this, we get the current text layer we have here. I'm going to actually show a demo of it because it's much more exciting when it's moving. How do I do that? Yeah. So I can now play around with having like an ambient light, a camera light, which is one that's like this, and we just end up with just a more kind of dynamic feeling shader. The problem with this is that it's still not very exciting because our text is flat. So like lighting looks good because objects are not flat, and that's how you can tell sort of like if something's round or something is square. If it's just purely flat, then a lot of the lighting effects are not going to do anything. So it kind of got me thinking, is there a way that I can make the text 3D to make this example a little more interesting? And it turns out that we can, because, and I think this is going to link onto one of the talks about text rendering tomorrow. So excellent. This will be explained tomorrow, so I can go really fast. We have this very cool technique that we're using Deck.gl called SDF text, where rather than storing the characters as just black and white pixels as masks, then we store them as this like smoothly changing field, which defines much more nicely how where the edge of the glyph is. So this nice little kind of test application from Fox shows this is what's actually being read by the GPU, and then this is what is being rendered. So what this essentially lets you do in the shader is kind of choose a cutoff in this field and then smoothly draw the actual glyph to the screen. And the added benefit is that we can also nicely draw an outline, because we can just specify sort of lower level of this fall off to be the outline just outside of our shape. But we can actually go one step further and think of this SDF as like a height map. So Here I'm basically drawing the same thing that we had on the demo before, except rather than going in a gradient from white to black, I've gone from green to red and actually added some contours to show more clearly like where the value of like 0, 0.1, 0.2 is. And this is actually beginning to look a bit like a map, like as a contour in like 3D space. And you can actually think of it as like that. So if you think of it as like representing a 3D space, you can then in the shader differentiate this 3D space, and with some maths fun, you can obtain the normal, and that's what you have here. So this is no like kind of pre-calculation. This has been done on like every frame at pretty much zero cost because we have all this data ready for us. So let's encapsulate this functionality in a new shader module, which we're going to add called Emboss. And this is going to provide a function that we're then going to integrate into our custom layer. So it's the same story as before. We're going to define a fragment shader with a uniform buffer object. The only difference is that we're going to add this new function that I'm not going to go through now. It's on the last slide if you want to have a look. And we can then inject this same module back into our enhanced text layer and just modify our fragment function to not hard code the normal, to get it from this function, and then send it to lighting. And then the one thing we mustn't forget is to modify the draw function, which has now got an extra prop, so we can control this from the outside. So here I just have a very simple single prop, which is the height of the bevel. Like how much are we raising? How much are we raising the text above? And that's going to control kind of the shape of it. So if I now go back to my demo, I'm going to make the text bigger because it's much easier to see. So we're going to go to London. Then I can switch to this kind of show normal sort of debug mode. And at the moment, it's completely flat. It's because the bevel height is 0. But as I increase this bevel height, then I'm going to see this text coming out. And if I go back to the standard view, then as I do this, it's going to give this nice kind of more sort of 3D look to the text. And now that we have this in place, then it's more just a matter of creativity to play with like the different lights. Like I can turn off this one. I can only have one type of camera light. I can change this color to be more, I don't know, specular, shiny. Yeah. I can now also play with some directional light. If I turn off the camera light, which is shining straight down, then what I've done is I've added 2 directional lights. One is coming from the top left. So this adds this kind of like highlight. And I can also fake a shadow by adding a light coming from the bottom right, which has got a negative intensity, so it kind of like darkens the shape. But yeah, I thought this was a bit of fun.
Felix, these properties uniforms, or can we apply?
Can they be specified by props?
Individual elements very next to me, like by every city in this case.
Oh, you're saying do they have to? Could they be specified on like a per text? Oh, you'd have to rewrite the shader, but yeah, I think if you could have an attribute that would specify them. Yeah, you would just have to kind of wire it up in like a different way. Yeah. So rather than sort of
we have like get line width, for instance, right? It can be or a function returns different values for different.
You mean a different value for each word, each city. Yeah, but for that you couldn't use the uniform because the uniform applies to the entire layer. You would need to instead add like a new attribute and make that be called for every single instance. Each kind of like word you have here, and then just pass it through. Yeah, but there's no reason you couldn't do that. Yeah, that is basically everything that I have. So thank you. So cool. I realize this is somewhat narcissistic that I have the whole world thanking me.
Randall Brooks.
So any questions, or I think I've run over a bit, so sorry.
And you showed the shader injection with WebGL. Is there going to be shader injection with WebGPU? Because
Well, I think they said no, so
how do we do it in future?
might have to write another shader. Yeah.